section 3.21, and we've been teasing this for so many weeks. We're finally working with multiple predictor variables. And in fact, we have estimating the regression coefficients, not just beta naught hat and beta 1 hat, as in simple linear regression, but we now extend the slope of the x1 variable to include two or more slope or additional, or one or more additional slope parameters, beta 2 hat to beta p hat. Again, the idea is to minimize the residual sum of squares. What are those? For each observation in our training data, we start changing changing the values of the betas until you minimize the sum of the squared difference between the actual data, the yi, and the model's predicted output. Where do we get this predicted output from? Well, that's calculated based on this formula. Let's have a look. The parameters are estimated using the same least squares approach that we saw in the context of simple linear regression. We choose a beta naught value, a beta 1 value, beta p value to minimize the sum of squared residuals. And that's formula 3.22. This will produce a hyperplane. What do we mean by a hyperplane? It's just a generalization of linear surfaces such as the one we have in the diagram on my screen when working with two predictor variables. In terms of diagrams, this is really as many variables as we can safely draw. You have your two predictor variables and your output variable, the one that you're trying to predict. And you've run out of dimensions. You can hardly draw, not in any conventional way. You can hardly draw more than three variables, x1 and x2, and we're regressing y on these two variables. What are these distances? I seem to remember using black yesterday. Each of the length of each black arrow that I'm emphasizing over here is the difference between actual and predicted. Actual are your red data points. Your predictions are based on the plane. It's no longer a line. It's still linear, but we're not working with curves anymore. This is a surface. Specifically, it has to be a linear surface. That means we're working with planes. In a three-dimensional setting, I'm reading the italicized text with two predictors and one response. The least squares regression line becomes a plane. The plane is chosen to minimize the sum of the squared vertical distances. Those were our black arrows between each observation, shown in red, and the plane. The values beta naught hat until beta p hat that minimize the RSS are the multiple least squares regression coefficient estimates. Quite a mouthful, right? All we're saying is multiple least squares regression. multiple, because we're using more than a single predictor variable, coefficient estimates. The betas are your coefficients. Estimates, we're drawing a hat. You're not saying that you know the true relationship, but you're trying to get close to that. Unlike the simple linear regression estimates given in 3.4, the multiple regression coefficient estimates have somewhat complicated forms that are most easily represented using matrix algebra. So here we're discussing how to actually calculate these estimates. For this reason, we do not provide them here. Any statistical software package can be used to compute these coefficient estimates. And later in this chapter, we will show how this can be done in R. And again, figure 3.4 illustrates an example of the least squares fit to a toy data set. Toy simply means it's not actually a real data set. In fact, a lot of these previous R sessions of ours this week have been with toy data sets. We've just been creating data that doesn't actually have any physical relationship to the real world. Table 3.4, and that's over here. And look, immediately we're discussing these p-values. What's interesting is this one is so much higher. If these are less than 0.01%, the intercept, the TV beta, the radio beta. Now look at the newspaper. Newspaper's coefficient is close to zero in inverted commas. We have a much higher p-value. So it might be the case that we're going to arrive at a point where we ditch the newspaper data. It's not necessarily adding any information that isn't already captured by TV and by radio. Table 3.4 displays the multiple regression coefficient estimates when TV, radio, and newspaper advertising budgets are used to predict product sales using the advertising data. As a single model, we interpret these results as follows. For a given amount of TV and newspaper advertising, so think of your partial derivatives, keeping these two variables fixed, keeping the x's fixed, the x TV and the x newspaper advertising fixed, spending an additional $1,000 on radio advertising leads to an increase in sales by approximately 189 units, comparing these coefficient estimates to those displayed in tables 3.1 and 3.3. We'll go back to them if necessary. We notice that the multiple regression coefficient estimates for TV and radio are pretty similar to the simple linear regression coefficient estimates. Let's have a look. So this is what we're doing here, and we have 0. We have, just go back to this page. Can I get it to zoom in? Apparently not. Here we go. So this time around, for those of you just joining, it's no longer simple linear regression, but we have multiple predictor variables. The specific example we're looking at, not this diagram, the specific example we're looking at has TV, radio, and newspaper as the three predictor variables. So imagine, just take a different example. Imagine you want to predict how long it takes you, just gonna mute everyone's mic just in case, how long does it take you to reduce your weight by 10 kilos, and you're on a new diet, you have a new fitness regime. Your target is, I would like to reduce my weight by 10 kilos. Is it going to take me a week? Probably unlikely. Is it going to take me a month? Is it going to take me 5 years? And your model, you may wish to take three variables. So, number of calories that you're consuming on a daily basis. So, your average daily calorie consumption, the number of, let's imagine that your fitness regime is strictly walking. So, the number of weekly kilometers of walking, and who knows, the number of hours of sleep that you're getting on a daily basis. So those would be your three predictor variables, assuming that there is a relationship. It's always the first thing that one would have to check. Is there actually a relationship? Does changing one of those variables have a statistically significant impact on the predictor, on the, excuse me, on the variable that you're trying to predict? Visually, it's a bit difficult to draw this information with three predictor variables. But what the book is doing, it's taking two of them, x1 and x2, and we are regressing y on these two variables. So just like we extended simple linear regression, where we were passing this blue line through our data, and we have now extended it to passing a plane through the data, you kind of need to think of what would it look like in higher dimensions. I'll be honest, if you told me describe if a line is for one predictor variable and a plane is for two predictor variables, what would it look like for three predictor variables, four predictor variables? My mind doesn't do a good job of visualizing such a coordinate system, but it's the same kind of, we're extending in the same kind of way that we have from passing a line to passing a plane through our data. We're going to use, what's it called? Least squares. We're going to use least squares to minimize the residual sum of squares. And apparently, if you apply this to the advertising data set, you end up with these four coefficients. Why is it four coefficients? You always have one parameter for the intercept term. That would be the output if your TV is 0, your radio is 0, and your newspaper is 0. So it's kind of telling you, if you don't advertise, if you don't advertise using TV, radio, newspaper, you're expecting that without any advertising, this is in thousands, I think, right? Maybe tens of thousands. I think thousands. You're going to sell roughly 3,000 units of whatever we're selling, microwaves, you name it, gym memberships. TV, for every $1,000 of TV advertising budget, you're expecting to increase sales by 46 units. I'm just moving the decimal point 3 times forward. And the model also suggests that for every $1,000 of radio advertising, you're expecting sales to increase by 189 units. Incidentally, this is linear regression. So the one drawback of linearity is that it treats each increase of $1,000, even if you're already spending $1 billion on marketing and there is no one left to sell to, everyone's already buying your products at the maximum rate. Linearity assumes that if you spend an additional $1,000, it's always going to increase by 189 units. In a later chapter, we're going to do generalized linear models, which do quite a good job, or at least attempt to address the limitations of chapter 3, which is all about linear regression. Now, what's interesting is the newspaper coefficient. One, it's negative, which is quite counterintuitive. So what? If you just look at the parity, unlike the other coefficients, a negative newspaper parameter is suggesting that for every $1,000 of advertising, you're actually going to sell 1 unit less. And granted, that could happen. Maybe people get so fed up. Maybe you're pushing the product to an extent that a bit of maybe reverse psychology, that your potential customers actually are influenced in the exact opposite way than what your marketing team would want. Although more interesting than the negative in front of the coefficient is its absolute size. It is 0.001, which may very well be the case that we conclude that in actual fact it is statistically insignificant, that we may just as well assume it is 0, and in fact maybe strip the newspaper variable, or I prefer a different word, just it's a redundant variable. There might actually be no relationship. In fact, going back to this p-value for the hypothesis testing, you may remember that the t-statistic in this example, if it's greater than 2, that means you have 95% confidence that this is truly not 0. This is truly not 0. This is truly not 0. Within a 95% confidence interval. This, its absolute value is less than 2. It's a lot less than 2, right? It's 0.2, so it's an order of magnitude less than 2. And in fact, we get a really high p-value. The highest it can be is 1. These are just probabilities. And you're nearly certain to reject the null hypothesis. No. You say, I don't have enough evidence to reject the null hypothesis. What was the null hypothesis? In this situation, the null hypothesis is there is no relationship between the y and the x. I've been speaking a lot about null hypothesis, and I never gave you a simple example. And I think we can do a lot worse than the one I'm going to mention. Imagine you have a coin and you toss it 100 times, and 60 of those tosses land heads. You can then set up a hypothesis. The coin is biased against the coin is not biased. And you would work with confidence intervals. So you would say, okay, if the coin is not biased, then how likely is it that out of 100 trials, 60 of them land heads? Is it just down to random chance? Or is the evidence so compelling? Is 60 considered so high in inverted commas that I'm actually going to reject the hypothesis that it's a fair coin in favor of the hypothesis that it is not a fair coin? Now, these are what the book is saying is that these two are actually quite close to when in the previous section we performed simple linear regression. Let's have a look. This is roughly 0.05 TV, and this is roughly 0.2. So let's go back, and it's these. And I've already forgotten them. But yeah, 0.2. But for newspaper, it's quite different because this is 0.05. We're a whole order of magnitude less. There are two zeros and then a 1. So, does it make sense for the multiple regression to suggest no relationship between sales and newspaper, while the simple linear regression implies the opposite? Let's look at the simple linear regression again. Simple linear regression, it was lower than radio, but it was still suggesting that there was a relationship. The t statistic is greater than 2. Let's see. And the book is answering in the affirmative. In fact, it does. Let's have a look. Consider the correlation matrix. We're familiar with the idea of correlation, even not necessarily in a mathematical setting. Correlation is, the hotter it is. I remember this is an example. I was meant to be presenting something on Solvency II, and this was an example from the audience. The hotter it is, the more ice cream sales there are. That kind of correlation. Notice that the correlation between radio and newspaper is 0.35. So this is correlation matrix. It's just telling you. You're taking the 200 observations, and you're saying sort of, let's look at radio against newspaper. You're saying that it's 35%. But that 35%, what does it mean? Well, I like to think of it this way. Let's say, that someone is in favor of whatever. Someone votes for a specific party. Then with that information, what is the likelihood that they are in favor or against a specific policy? I don't know, nuclear disarmament, foreign intervention, foreign aid, democracy. That's how I like to think of correlation. So if you know what has been spent on radio advertising in a specific, do remember what are our data points in we need to go way back, way back, I think. Take it way back here. Remember, we have 200 observations. Each observation is a market. So think of it as a city, a country, specific region. And the correlation is telling you, if you know that, for example, you've spent 20,000 on 20,000 in these markets, then for these same markets, for example, I don't know, Germany, Spain, Italy, if you then find them over here, Italy, Spain, they need to be on the same line. There's the same number of sales, and Germany. Then how likely am I to predict what's being spent in those same three markets in terms of newspaper advertisement expenditure? It's probably the easiest way. Of course, I'm open to suggestions, but I've always found it probably the easiest way to think of correlation. So we're looking at correlation over here. Notice, of course, t if you take a variable with itself, the correlation is 100%. If I know what's been spent on TV, well, I know what's been spent on TV. If I know what's been spent on radio, I know what's been spent on radio. More interesting. Ah, by the way, these are blank, but it's just the same values that you have over here. So your correlation matrix is always symmetric about the leading diagonal, meaning if we use color blue, then this would be blue. So all I'm saying is the correlation between newspaper and radio, and the correlation between radio and newspaper, that's the same value for obvious reasons. It's a symmetric relationship. So it's 35% between radio and newspaper. Let's see what the book is getting at. This reveals a tendency to spend more on newspaper advertising in markets where more is spent on radio advertising. All it's saying is it's a positive correlation. Now, suppose that the multiple regression is correct, and newspaper advertising has no direct impact on sales. But radio advertising does increase sales. Then in markets where we spend more on radio, our sales will tend to be higher. And as our correlation matrix shows, we also tend to spend more on newspaper advertising in those same markets. Hence, in a simple linear regression, which only examines sales versus newspaper, we will observe that higher values of newspaper tend to be associated with higher values of sales, even though newspaper advertising does not actually affect sales. And I think this is the most important sentence, the one that's coming up. So newspaper sales are a surrogate, also known as a proxy. Newspaper sales are a surrogate for radio advertising. Newspaper gets credit for the effect of radio on sales. And this is why, or this may be the reason why you ideally want to define it more rigorously, but this is why the newspaper coefficient is practically zero over here, because in actual fact, although in simple linear regression, when we were only looking at the impact of newspaper advertising on sales, we had a statistically significant 0.055 slope parameter, beta 1 hat. In actual fact, now that we're allowing for more predictor variables, it would appear to be the case that now that we're allowing for radio, it's actually radio that's driving the sales and not newspapers. I'll give you a really simple example. So there's a statistic that says that crimes that that criminal activity increases on days where it's a full moon. Okay, interesting, interesting. So the data is suggesting a correlation. Now notice that's simple linear regression. Your X variable is phase of lunar phase, and your vertical axis is criminal activity. And you can measure criminal activity. It's very, very easy. Just look at publicly available police reports. You can see on this day, there were so many police reports. There were so many people that were maybe the next day charged with some kind of criminal offense. So that's simply linear regression. Now, in actual fact, you should allow for maybe more variables. And the statistic, you can quickly explain away the apparent relationship quite easily. Maybe you want to take a few seconds to think, why should criminal activity increase when we have a full moon? And at least what I've heard is it's quite a common sense explanation, although it wouldn't have necessarily occurred to me anytime soon, unless I heard the explanation. Well, if it's a full moon, there is more light. There is more light for burglars to, for example, see at night without using torches and other artificial sources of light that might give themselves away. So it's not actually the fact that the moon is in some way affecting our behavior. It's just simply a case that if you have more hours of light, if you have a higher in light intensity, then you have more opportunity to perhaps navigate during nighttime, and which kind of facilitates behavior which might be criminal. That's possibly the simplest example I can give. Now how useful it is, if it makes sense, I guess that depends on each one of you. But this is the idea. This is the idea that including more variables, refining your model, going beyond simple linear regression, means that we might actually spot certain variables that we initially may have believed drive to some extent the variable that you're trying to predict, and actually conclude that, in fact, that relationship is a negligible one. As you can see from this, it's practically zero. Do we conclude that it's zero? The t-statistic tells us yes, because instead of a very low p-value, we have a very high p-value. The highest is 1, so it's really, really close. So newspaper sales are a surrogate for radio advertising. Newspaper gets credit for the effect of radio on sales. The slightly counterintuitive result is very common in many life situations. Consider an absurd example to illustrate the point. Running a regression on shark attacks. You're joking. Did I mention ice cream sales only 10 minutes ago? It's not the same example, but I was actually going to say, I was instead of the lunar example, I was going to take sort of given, yes, of course, the true relationship is just you're not allowing for heat, right? You're not allowing for seasonal, temperatures. So consider an absurd example and sometimes they are the best examples, an absurd example to illustrate the point. Running a regression of shark attacks versus ice cream sales for data collected at a given beach community over a period of time would show a positive relationship similar to that seen between sales and newspaper. Of course, no one has suggested that ice creams should be banned at beaches to reduce shark attacks. In reality, higher temperatures cause more people to visit the beach, which in turn results in more ice cream sales and more shark attacks. So it's temperature that's driving both of them. If you ignore temperature, it would appear that one is driving the other. And one of these days, unless I show it to you right now, one of these days remind me, is it Nicolas Cage? I'm not sure, but I'll go into it. Nicolas Cage, and was it pool deaths or pool drowning? Let me see if I have an image, and I'll just share it very quickly just to make it a memorable example. It's a slightly small chart. Not sure if I can zoom in. Actually, it seems to be making it worse. And look, you have, is this the number of films he published? So there's a 66.6. That's considered quite high in the field, correlation between the number of people who drown by falling into pools and the number of Nicolas Cage films released that year. Now in this case, I would imagine it's even worse than the shark attacks and the ice cream. At least over there is a third variable driving both of them. This we can only imagine is purely coincidental. If you look at enough data, you will have these coincidences. However, unlikely if you look long enough, you're bound to find something. Okay. Hopefully that gives you an idea of correlation. A multiple regression of attacks versus ice cream sales and temperature. This is how you should be doing it, right?
So,
yes.
What is a t-statistic?
What is a t-statistic? We discuss it in yesterday's session and the one before. All you need to know for the time being, and thank you for asking, is that when we perform these hypothesis tests, normally there is a statistic, not necessarily a t-statistic. When we say t is just a distribution. Let me open a new file. We've been working quite a bit with normal distributions, where I can say heights in wherever, Malawi, and these heights for women. So we'll do women heights in Malawi, and we have our data, and the data would suggest perhaps that the distribution of women's heights in Malawi in a specific decade, and in the 1990s, follows a normal distribution, and I can just generate maybe 100 of these heights. So I tell R distribute 100 with a mean of 175 centimeters and the standard deviation of, say, 20. You do it, and we can now do a little histogram. That's your histogram. You could do it as a box plot as well. Box plot. And we'll draw it horizontally. Right? So you have some outliers over there, and 50% of the data, is between these two values. Okay. So this is your lower 25%, your upper 25%. The green is the middle 50%. Think of it as the mainstream. Now, the normal distribution is just one of many, many different distributions. Another one is the T distribution. We can have a look at it very quickly in Wikipedia. It probably goes by many names. To my knowledge, Fisher. This is like one of the most preeminent biologists and really sort of like founder of, let's do T distri. Wow. Okay. I mean, I just want something similar. T distribution. In fact, yes, it's also known as students T distribution, and I think it's student. It was possibly Fisher not giving, not wishing to reveal to the competition. Don't ask me what the competition was. No, it wasn't Fisher. It was this individual, and yes, it had to do with beer. So I think it was they were like testing. I don't know, and it was published under a pseudonym, not to reveal. I guess since this guy was working at a brewery, not to reveal that he was using statistical tests to perhaps improve. I don't know if it's a legend, but that's the story I know. To improve the product. If you look at history, yeah. Anyway, it's probably somewhere here. Although Fisher is mentioned, I see. Okay, so Fisher gave the name of students distribution. It is just another probability distribution, and notice when it depends on one parameter. What do I mean by a parameter? So the normal distribution depends on two parameters, mu and sigma. The T distribution depends on a single parameter. So if you had to do it, I don't know, random values, and you do, instead of R normal distribution, R T distribution, that's not what I want. How many values would you like to generate? Let's generate 100. And then it just asks you for the degrees of freedom. Wikipedia is using Greek letter nu. Is it mentioned in the very, yeah. It's known as the degrees of, freedom. Anyway, this is a very long way. This is a very long explanation, but I'll just let's do a box plot. Random values. That's your box plot. Okay, so it's, you have your median, which is below 0. When we say a T statistic, it just so happens that to test the hypothesis that there is a relationship between X and Y. So for example, that there is no relationship, excuse me. The null hypothesis is there is no relationship. To test whether there is no relationship between sales and newspaper expenditure, newspaper advertising, you calculate this value. And this is known as a T statistic. We're going to be doing this, those of you who are going to set CS1, or you're going to have inference in perhaps your second year of your university course. There are all these different statistics. There are F statistics as well. There are many different statistics that are used to test specific hypotheses. It just so happens that we use the t distribution, not the normal distribution, not the binomial distribution, but the t distribution to test the significance of our estimated beta naught hat, beta 1 hat, beta 2 hat. If you get a very low t statistic for any of these, then what it might mean is that you may consider excluding the variable from the model. It's not helping, and this is what I mean. Small is close to zero. The t statistic is small. What do I mean by small? If it's 30 degrees of freedom, don't ask me from where I got the 30. If it's 30 degrees of freedom, this is what we did yesterday, in fact, you would only assume that this is not zero. You would assume that this is not zero, that there is a relationship if the t statistic has an absolute value greater than 2. And over there, I'm assuming you're happy being 95% confident. That's all we mean by a t statistic. I mean, I say that's all we mean. It's actually quite a difficult, something I get tripped up on a weekly basis. Do I reject the hypothesis? Very often I find myself consulting my old notes. Right, and I think let's see, a multiple. This is what we were doing. A multiple regression of attacks versus ice cream sales and temperature. Okay, so your pink, that's your predictor variables. That's your x1 and x2. Your green is the vertical axis, the y variable. The red is the plane that you're going to pass through these points. Reveals that, as intuition applies, the former predictor is no longer significant. So ice cream sales is not actually a significant predictor. You could go so far as to say it's irrelevant to predicting the number of shark attacks. This is now that we've included temperature. Same thing in what we're doing over here. Now that we've included TV and radio, it would appear that newspaper expenditure, newspaper advertising budgets do not actually influence the number of sales. Okay, some important questions. When we perform multiple linear regression, we usually are interested in answering a few important questions. Is at least one of the predictors, x1 to xp, useful in predicting the response? Do all the predictors help to explain why, or is only a subset of the predictors useful? This is where we saw that maybe the newspaper expenditure isn't that helpful. How well does the model fit the data? Given a set of predictor values, what response value should we predict, and how accurate is our prediction? And let's start with question number 1. This is where we're going to discuss. Interesting. It's no longer a t statistic. And I mentioned F statistic earlier. Let's have a look. This is another type of distribution. And can we get it to work in R? So what if we say F randomly generated values, and we say RF. Interesting, interesting. Okay, so apparently we need a lowercase. How many would you like to generate? Let's generate 100. There are 2 degrees of freedom. There are 2 parameters for F distributions. And I'll say maybe 5. I'm just inventing. I'll maybe say 10. And here you go. These are your 100. You can summarize. So we have that minimum and that maximum. Visualizing is definitely helpful over here. With horizontal is true. So if you take a degree of the first degree of freedom as 5 and the second degree of freedom as 10, apparently, I would have never guessed this, but apparently we get this distribution that most of the data, well, 50% of the data is between around 0.5. Well, we can see them over here, right? Between 0.48 and 1.64. And then you have sort of your outliers. We really shouldn't use the word outliers, but in many ways, it's easy to explain. Look, by the way, you can think of this. I can see a lot of applications for this in the world of insurance, where this could be, why don't I multiply by, can I multiply by 10,000? Multiply by 10,000. Okay, so most of your, by the way, the distribution changed from earlier. Since I didn't set a seed, it is generated 100 totally new values. And most of your insurance claims would, well, typically you'd want them to be on the low side, so between 0 and 10,000. And then you have larger insurance claims, but at lower probabilities, although it seems to spike a little bit over there. So we're no longer going to use a t-statistic. Apparently, a t-statistic is used in simple linear regression. Now it's time for an f-statistic. Let's have a look. Recall that in the simple linear regression setting, in order to determine whether there is a relationship between the response and the predictor, we can simply check whether the true value of beta 1 is 0. In the multiple regression setting with p predictors, we need to ask whether all of the regression coefficients are 0. Interesting. So what we're doing is we're taking them all at one go. I guess after all, over here it said, is at least one of them useful? Okay, so the null hypothesis is that none of them are useful. They are all 0. Their slope parameter is 0. And if you know your logic, what's the opposite of all of them? Well, the opposite of all of them is not none of them. The opposite of all of them in logic is at least one of them, right? If I say, I haven't visited any South American country, the opposite of I haven't visited any South American countries, that I have visited at least one of them. As in the simple linear regression setting, we use a hypothesis test to answer this question. We test the null hypothesis, H0, which states each true parameter is 0 versus the alternative, at least one beta j is non-zero. This hypothesis test is performed by computing the F statistic, which unfortunately uses TSS, which we had done in one session, but very quickly towards its end. We might need to double back, but let's see how much we can push forward. So you're going to calculate the F statistic. We have minimized the RSS, so that's going to be a specific value. We know the number of predictor variables. In the case of the advertising data set, we're using 3: radio, newspaper, and TV. We'll have to just refresh our memory what the TSS represents, and N is your number of observations. In this advertising data set, we're looking at 200 data subjects. They are not people. They are not, I don't know what. They are the different markets in which we have advertised. Think of advertising across Facebook, for example. Facebook will very, very quickly, same thing with Google, they'll give you a breakdown of where your monthly advertising expenditure has gone in terms of geographical segmentation. Okay, so first of all, table 3.6 has more information about the least squares model for the regression of a number of units sold on TV, newspaper, and radio advertising budgets in the advertising data. Other information about this model was displayed. That's when I think we estimated the betas, right? In table 3.4, which was these over here. So these are the individual coefficients. It really gets interesting when you do this in R, but the theory is quite important. So what do we get? We get a residual standard error of 1.69. And let's remind ourselves, what is the residual standard error? Residual standard error is looking at your error term. And was it... Yeah. Remember when we were calculating these confidence intervals? And we needed sigma for the standard error for beta naught hat, beta 1 hat. What is sigma? Sigma is the standard deviation of the error term. So sigma squared is the variance of the error term. You want it at, the smaller it is, the better. The closer the data points would be to your true line, your true, the true linear relationship. Now in practice, you wouldn't know sigma. No sigma, would you? Just like you wouldn't know the true relationship. Although we have been coding recently where we assume that we know these. You assume that you know your true beta naught, your true beta 1. You assume that you know your error terms standard error. In practice, you don't actually know it. So instead, we estimate the sigma using the residual standard error. It's trying to capture the variability in your error term. And that's defined as the residual sum of squares divided by n minus 2, square root everything. So that's your residual standard error. Then we have this r squared, which again, it was one of those items that we mentioned, but only very briefly. if necessary, maybe tomorrow we'll spend one lesson on, or one session, I should say, on TSS and R squared. But what's interesting is that we have an F statistic of 570. Now you're going to use that 570 to calculate the p-value. And we can probably end on this point. It will be interesting to see what the p-value actually is. Unfortunately, I'm not seeing it. And maybe I'd be surprised if they don't calculate it. So let's have a look. Let's have a look. A larger F statistic is needed to reject. Let's end it over here. Thanks everyone, and we'll meet next session.